Hello ELT132, this is Roger Young, and this video is a discussion about parity. Now parity, as I've said right here, that basically is used to check to see if what has been received is what was sent. I mean, think about it. If you're doing a transmission from one circuit to another one, or one computer to another one, you have to have some kind of check to make sure what was sent is what was received. So remember, lines are not perfect, transmission lines. So there is noise, okay? So you have to check for that. This is a discussion of one way to check for that. I'm sure there's more ways. The other thing I want to make sure that you understand is what we're going to discuss today, and as I'll show you, this method of parity is not perfect, all right? In other words, it is possible for a transmission of data to be received, and the checker on the receiving side will think that it's good, is what was sent, when actually it was not what was sent, and I'll show you that. So first, let's just go over parity, right? There's two types of parity. We have what's called even, right? Even parity, and we have odd parity, all right? Now what this basically refers to is the number of ones. I'm just going to put this number of ones, right? And I'm going to say this is even. It's going to be 0 ones, or 2 ones, 4, etc. It's going to be an even number of ones. Odd is going to obviously still be the number of ones. However, that's going to equal 1, 3, 5, and so on. So let's discuss the circuit, and I think you're going to have a better idea about what's taking place, okay? So let me just get rid of this here. That's my scratch area because there's not a lot of space on here. Let's say we're transmitting some data, and it's just 2 bits, A and B, okay? Actually, we're going to transmit 3 bits because you have to account for the parity bit. But when you look at this is an exclusive OR gate, and I wrote the truth table right here for you. So if A and B are both 0, right, the output's going to be 0, isn't it? If A and B are both 1, the output is going to also be 0, correct? But if A is 1 and B is 0, or A is 0 and B is 1, which means it's one of these cases right here, the output is going to be high, okay? So we're basically counting the ones, aren't we? If the number of ones are even, in other words, if it's 0 or if it's 2, remember you'll have a 1 in A, a 1 in B, that's 2 ones. 2 is an even number. The parity bit is going to be 0. However, if the number of ones is an odd number, or 1 in this case, in other words, if A is 1 and B is 0, or A is 0 and B is 1, in either case, there's an odd number of ones that are being sent, the parity bit will be high, and that's shown right here in your truth table, all right? So that's what's being sent in a serial transmission, all right? So usually these transmissions are grouped, and suppose it's grouped in groups of 8 bits. Well, the last bit is going to be your parity bit, okay? So it's going to look at the prior 7 bits, it's going to count the number of ones, and then it's going to determine if it's an even or odd number, and just like what we talked about, and it's going to make the parity bit either 0 or 1, and that whole byte's going to be sent. But by the way, they could be different. It's discussed in your text. I'm just making a simple example here. So it's sent, suppose it's sent across the ocean over to England. Now they have a receiver here, right? Here's your parity checker. So it's going to check A, and it's going to check B, and it's going to generate a parity bit right here, just like when it was generated back at the transmission. Now it's going to compare the parity bit that you just generated to what was received. They should be the same. If the data that was sent is the data that what was received, these should be equal. And if they're both equal, whether they're a 0, 0 or a 1, 1, the output should be 0, right? That's where this comes in. Okay, that means what was received is what was sent. It was a 0. Got it? But if these differ, in other words, if this was a 0 or this was a 1 or this was a 1 or this was a 0, it would be one of these cases, in which case the output would be a 1. Now if it's a 1, then it says there's an error. All right? That's basically parity. Now, let me say something to you real quick, or explain, I'm sorry, why this is not perfect. If you sent a group, suppose you sent a group of 4 bits, all right? Let's draw this down here, right? 1, 0, 1, 0, all right? That's even. I'm going to just put even over here, because the number of 1s, there are 2 1s, that's an even number. Suppose it sent this, 1, 0, 0, 1. Guess what? That's also even parity, isn't it? So if these were both even, this would come out low over here, because these inputs would be identical. However, are these the same? Is this the same information that was received as what was sent? No, it's not. Look what happened. This bit changed from a 1 to a 0. This bit changed from a 0 to a 1. There's the rub, okay? If 2 opposite bits, or 4 opposite bits, however many bits, if the same number of 1s changed to 0s and the same number of 0s changed to 1s, then the number of 1s is going to stay as what was transmitted, and so it's not going to be caught by this checker. That's the key thing I wanted to make sure that you understood. The probability of this happening, I don't know, the longer the string of 1s and 0s are, the less of a chance it's going to go through. But anyway, that's the problem with it. Now, another thing I want to make sure that is understood is we just did two lines. We could do 4, and this is an example of a 4-bit or a nibble parity checker, right? So you have A and B, right? If they're even or odd, right? If the number of 1s, is even, this is going to be 0, isn't it? And if the number of 1s here are even, this is going to be 0 right here. Why don't I just write a 0 here, right? And guess what? If 0 is going to be going in here, what do you have? You have a 0 on the output, right? Now, on the old modems, they had a little switch, even or odd parity. They don't have that anymore. You don't have to worry about that. But when you used to go over telephone lines and everything was serial like it was over the phone lines, you had to have a modem, okay? Well, this is what the switch did. It was for your checker, right? So whatever you received, you would then compare it to what parity you should have, right? And then it's just the same thing with what's going over here. You're going to compare your parity that was sent to what you receive, and then you're going to have an output right here. And then that would tell you if your parity matches, and obviously if there was an error right here. All right. I hope this has helped you understand parity better. And if you have any questions, we feel free to bring it up in lecture. Thank you.